There are all sorts of useful approximations we can do to whatever the true physics is. Every single physics equation I've ever taught at MIT is also just an approximation of whatever the true equations are, because we don't know what the true equations are, but we know that we haven't found them yet, because the equations of quantum mechanics and the equations of general relativity, they don't talk to each other.
Max Tegmark, thank you for accepting my guilt-laden offer to join me on my birthday for this episode of Into the Impossible.
It's such a pleasure, and happy birthday again. I wish you all the best for a very successful new orbit around our sun.
I think it's been about 10 years since your very first book came out, Our Mathematical Universe. And I love this book for many reasons, not the least of which because my PhD thesis experiment is featured prominently therein. But I want to actually do what you're not supposed to do, which is to judge a book by its cover. We've always done that on this podcast in recent years. And that's to take people through the idea, the title, the subtitle, and the cover art. Talk about the title of the book, how it came to you, Our Mathematical Universe, and then I have a provocative question based on this. My quest for the ultimate nature of reality. How'd you come up with that?
First of all, I actually do have a little copy handy here. And so here you will recognize, of course, our universe, as we will probably discuss again shortly. And our universe, rather than the universe, is a subtle hint that I think there are also other universes, and we shouldn't be so arrogant and just refer to our own one as the universe, just like we don't refer to the spinning ball in space we live on as like the planet. It's our planet. And then the mathematical there is kind of the real kicker, because I'm making this very radical argument in the book that our universe is, in fact, very mathematical, in fact, completely mathematical, in the sense that we're actually inhabiting an enormous mathematical object, and that's a good thing, not a bad thing, because that gives us humans even more opportunities to discover patterns and regularities and make more predictions and figure out how stuff works and use that to build awesome technology that can empower us.
Very good. Well, I want to also take a quick look through my book, my first book at least, Losing the Nobel Prize, where Max appears on page 4. And I wasn't there at the press conference at Harvard Center for Astrophysics, which I described the reasons behind that in the book. But I said I could see Max Tegmark, MIT physicist, reporting live from the event. I am writing this from the Harvard press conference, announcing what I consider to be one of the most important scientific discoveries of all time. Within the hour, it will all be over the web, and before long, it will lead to at least one Nobel Prize. One of the claims that you talk about in this book is this lovely connection between the theory of inflation and the multiverse. And your neighbor at MIT, Alan Guth, who will not return my emails for some reason. No, I've met him many times, and someday I'll have him on the podcast. He has said that in most models of inflation, the multiverse is present. I want to ask you a question. In the 10 years since this book and since Bicep 2, exactly 10 years ago this year, have you changed your mind about the probability that the multiverse exists, or has it gotten stronger or weaker?
Before I answer the probability question, thank you for bringing back this fond nostalgia of that press conference. I still remember how excited I was. I was so stoked that I even told my wife, who's not the physicist, that you have to come with me to this, because this is a once-in-a-lifetime event, and it really was intense to hear this announcement. That was before these gravitational waves bit the dust, as you're painfully aware of. But that doesn't in any way take away from the excitement at the time, right?
No, in fact, it might mean that it's not a once-in-a-lifetime press conference.
That's true. Maybe it'll happen again. I would say that my probability for betting that inflation did happen has stayed quite constant, but the probability I would assign to there being that kind of conclusive proof anytime soon has gone down quite a bit, unfortunately. I felt inflation, basically this, for the listeners, the most popular theory for what put the bang into our Big Bang, it had predicted a whole bunch of stuff. Predicted that there was a Big Bang, check. That our universe was expanding, in a very uniform way, check. It had predicted that if you measured whether space was curved or not, you would find that it was very much not curved, check, to 1% accuracy. And it had predicted that the clustering we see in our universe and in the cosmic micro background, the ratio of big clumps to small clumps was very much according to the simplest model of inflation. There's this number n, you know, that the simplest model predicts should be 0.96, and it was measured by people, including experiments where I had been involved in analyzing them, to be about 0.96 with pretty small error bars. And it also predicted that there was this other thing that should be there. There should be these ripples in the very fabric of space-time itself, known as gravitational waves, and they should be there at a level that corresponds to this number r equal to about 0.15 or so, and it would have just been the icing on the cake. And then your paper came out that said, we found it, it's about 0.15, 0.16. And sadly, right, not only did you discover that your experiment was contaminated, that sucked, that was sad for you, but for the community and for me, what was sad was what happened after that, which was that subsequent experiments actually got much more accurate and said, no, there is no signal there, even at a much lower level. So now, if inflation did happen, it's a more complicated kind of inflation. It's not the absolute simplest, which should have been such a one and done, open and shut case. I still think it's very likely that inflation happened, but since whatever inflation it was shy enough to not leave as much traces behind, it just makes it so much harder for us to really clinch it experimentally.
Yeah, I agree. And one impression that I've loved to get from you in the context of the book, Mathematical Universe, you know, towards the end when you classify the different levels, and I recommend this book to all my students and even non-experts, but you classify different levels of multiverses. And the level 4 one is, of course, the most controversial one. It's the one that suggests that perhaps all or many different types of mathematical structures would exist, sort of a parallel to me of the level 2, which suggests that different physical constants could be manifest. You could have the speed of light be 10 meters a second in one universe, and then 299,000 in another one. What I've wanted to ask you for a long time, reading it again, is why stop there? I mean, were you bold enough? In other words, why not include all logical structures as well as mathematical structures? In other words, in some universes, modus tollens exist, and in some universes, you only get modus ponens. So is it possible that the laws of logic would be subsumed within the laws of mathematics, or am I totally in left field here?
Let's work our way up to that question, but maybe we should just first remind ourselves what these 4 levels are. So they're ordered by increasing diversity. In the level 1 multiverse, which is just more space than the part of space that we can see, if that exists, which inflation generically predicts, right, then there are many other galaxies with solar systems that look exactly like ours. And we even with a copy of Brian and Max having a conversation and so on, and they might look like us, but they might have learned different things in history class because the particles in their neck of the woods started out in slightly different places. So maybe a different country won World War II, or someone else won the presidential election, whatever. But they would learn the same things in physics class. They would still learn that there are 6 kinds of quarks, for example, that make up all the particles. If you go to level 2, on the other hand, there is more diverse. String theorists predict that there are many, many different solutions for uniform space. And even if string theory is wrong, most complicated equations like loop quantum gravity, etc., try to describe space and the stuff in space. They have many solutions. And inflation, right, is so violent that it's going to make a massive amount of space of each kind. So if you go somewhere else in the level 2 multiverse, you might actually also learn different things in physics class, that there are only 4 kinds of quarks, or maybe there is no electromagnetic field at all. Maybe people can't see each other because there's no light there, etc. And then there's the level 3 one with quantum mechanics, which is weird in its own lovely way, but actually not more diverse, as it turns out. And then in level 4, as you mentioned, where you have all the different mathematically possible theories being equally real, there you can have more extreme differences. Maybe time comes in discrete chunks, like in a computer game, or there are lots of fascinating possibilities. As to your question, I will argue that what you call different logics, again, not having modus ponens, having modus tollens, and other things, are actually included in the level 4 multiverse, because most people have a too narrow view of what math is. I think a lot of people think of math either as just a sadistic torture device for making students in school feel bad about themselves, or as a bag of tricks for manipulating numbers. But if you talk to a modern mathematician, they study all sorts of mathematical structures defined by all sorts of different axioms. You can study a mathematical structure where there is modus ponens and where there is not, just in the same way as you can study a space that satisfies Euclid's axioms, where two parallel lines stay parallel forever, or where two parallel lines eventually meet. And so that's still very much included in the level 4 multiverse. Basically, everything that obeys some self-consistent set of axioms is welcome to be part of the level 4 multiverse.
When you look at the laws of physics, and I want to get into, in particular, quantum mechanics, it came upon, this very strange fact, which obviously you know and every physicist knows, this so-called quantum mechanical commutation relations that lead to the uncertainty principle, the incompatibility of simultaneously measuring position and momentum. And lesser known, is that these same things exist in classical mechanics, that they're called Poisson brackets, and they're basically commutation relations. But the only difference, and that somebody in 1850, Hamilton himself, Lord Hamilton, could have predicted quantum mechanics if he only knew about the square root, or because it's square root of -1, rather. Because really the only substantive difference is this imaginary number, which comes from a square root. And furthermore, Dirac could have taken the classical wave equation, added effectively what's the square root of a matrix, and gotten the Dirac equations that predict antimatter. My question for you is, do all mathematical structures exist in this universe? In other words, if we just took everything, every Grassmann algebra, every, look for everything and say they must exist somewhere, is that also a lunatic statement by yours truly?
No, it's an interesting statement. I would say no, but, and here's the but. So when I say that our universe is a mathematical structure, what I mean by that is that our universe has only mathematical properties at the fundamental level. There is one very particular kind of mathematical structure, which is our universe, and we live in it. However, a fascinating fact about math is you can very often approximate one mathematical structure by other simpler ones. So for example, if you have a sphere that's really big, you can approximate a little piece of it as a flat plane, because you don't even notice that it's curves if you don't go more than an infinitesimal piece of the way around. And in the same way, we have found that there are all sorts of useful approximations we can do to whatever the true physics is. We can approximate it with classical mechanics or special relativity if gravity isn't too strong, stuff like that. In fact, I would be more radical and say that every single physics equation I've ever taught at MIT is also just an approximation of whatever the true equations are, because let's be honest, Brian, we don't know what the true equations are, but we know that we haven't found them yet, because the equations of quantum mechanics and the equations of general relativity, they don't talk to each other. They don't get along. No one has managed to convincingly unify them yet. So even though our universe is actually just one mathematical structure, a whole host of different mathematical structures are actually very useful approximations for different aspects of the physical world we live in and different parts of them.
One question that I have is, first of all, as a master teacher, as you are, I've learned a tremendous amount from you. You were incredibly gracious during my graduate career and sort of a surrogate advisor, even though you're only a couple of years older than me. Still, you've always been an avuncular figure and a master educator. I want to ask you about what you think your theoretical students, although you've worked on experiments, including mine, but what do you think a theoretical graduate student, theoretical physicist, whatever, should learn? What should she or he learn about the craft of experimental physics?
The first thing, I think, is to learn that there is this love-hate relationship between theory and experiment in physics, which is incredibly productive ultimately. Sometimes theorists hate experimentalists for destroying their otherwise perfect-looking theories, and sometimes experimentalists can be quite annoyed with theorists. But even theorists sometimes who have incorrect theories will sometimes inspire experimentalists like yourself to work super hard to build an experiment they wouldn't otherwise have built, and then discover something else which they wouldn't have found at all if that theorist hadn't been wrong. And it's so obvious that physics has come as far as it has only because of this rough and tumble interaction between theory and experiment. So I would encourage anyone who's going into theoretical physics now to not only be quite up to speed on what's happening in experiment and what experiments might be coming down the pipe soon, but also to make friends with some experimentalists, but both in order to have a healthy distrust of experimental results, and also to encourage the experimentalists to look for stuff they might not otherwise have. You know this joke, Brian, that when a theorist publishes a paper, they're the only one who believes it, and when an experimentalist writes a paper, they're the only one who does not believe it.
That's right. And the equivalent joke from Arthur Eddington: never believe an experimental result until there's a theoretical prediction that backs it up. Yeah, it's also true. It's another quote or canard or trope is, a theorist only has to have one idea in his or her life to make a whole career, and an experimentalist only has to have one wrong result to ruin his or her career. But I'm proof that that's not actually true. And along the lines of the experimental, I call it the experimental minimum, to use our friend Lenny Susskind's terminology. What is the minimum about an experiment that you should know? I tell my experimental students that you don't have to do theory, but you have to know the theory. You have to know it at the level of a graduate student, in theoretical physics. But I don't expect, some of them do create new theory or theoretical contributions or analysis frameworks. But the reason I'm curious to get your opinion about experimental physics is because, the late, great Jim Simons, was an MIT grad who you knew, and I, of course, it was like a father figure to me. He passed away this past May, and we all mourn his loss. But, he funded generously, over $100 million to projects that bear his name that I've been, granted the ability to co-lead with my colleagues. And I want to know, when should we stop looking for inflation and the concomitant multiverse? I mean, how much should we dedicate? The U.S. is poised, potentially, hopefully, to dedicate maybe $1 billion to the so-called CMB Stage 4 experiment. Currently has a little hiccup in that the South Pole has been ruled out as a site for a little while, but who knows? Maybe we'll put it in Sweden. But the point is, Max, when do you stop an experimental search?
I think inspired by Simons, since he made his money in finance, it's good to have a balanced portfolio that we invest our energy in as scientists, not put all our eggs in one basket. Sometimes it makes sense to really go hard on big, expensive experiments, be they CMB experiments that are expensive, like the Planck satellite, or be it the Large Hadron Collider. But at the same time, it would be terrible if that's all we did, and we never gave $100,000 here for someone who wanted to try some new little crazy tabletop thing, right? It's when you have the balanced portfolio like this, that's when you do by far the best. And we need to be humble and realize that we don't know what experiments are going to find. And even if we think we do, as well as anyone, sometimes things nature has a way of just totally surprising us. So I would say, as long as humanity is alive and kicking, we should continue trying to understand our universe better. We should take a broad view across the board and ask, what are the types of experiments that we can do, and how much do each cost? And then do a lot of the cheap ones and some of the experimental ones based on our best understanding, and should regularly update this. If you take the longer view, I think nature has shown us that she is full of surprises, and whenever we've managed to go in order of magnitude into the unknown in any way, either looking at an order of magnitude farther away stuff, or an order of magnitude smaller stuff with microscopes, or orders of magnitude off towards longer wavelengths or shorter wavelengths, or with new kinds of radiation, almost infallibly we get surprised, right? people said, "Oh, it's such an idiotic idea, to look for X-rays in the sky. What are you expecting? There are going to be dentists out there, And then people discover, oh, the sun is giving off X-rays. There's X-rays all over the place. When Leeuwenhoek looked in a microscope, he found new tiny life forms. That was not what he was expecting to find. So I think we have a moral imperative, frankly, whenever we have the technological ability to push an order of magnitude into the unknown in any way, to do that if it's not prohibitively expensive. The discovery of extrasolar planets is a spectacular example of where science was actually set back. We delayed the discovery of planets around other stars by over 10 years because the astronomers listened too much to theorists who said there cannot be any hot Jupiters. Don't build these kind of experiments because they're not going to find anything.
My thumb is very busy right now holding up good old Albert, but if yours is free, please go ahead and hit that like button. And don't forget to subscribe. It really helps us with the algorithm. Similarly, that kind of preempted my next question, because I did want to get into talking about the search for extraterrestrial life and perhaps intelligence. And maybe it is a good segue to just do this now. And that's the following. Suppose your colleague and my friend Sarah Seeger is working on TESS or JWST, and she spies through her spyglass, this binary planet system. Imagine there's a binary planet system. And one of these two planets, both of them, in the habitable zone of a G2 subdwarf yellow star, just like our sun. And they're both, these planets in the habitable zone, very close to one another. And she spies them and she observes them with the Webb telescope. And she zooms in and she can see that there's, creatures and they're using, these kind of silicon slabs with glass on top, and they're emitting infrared radiation, waste heat. And then she gets the idea, well, that's technology. There's not only life, but it's extraterrestrial intelligence, Max. And that planet's name is Hetarth. And then she says, well, I want to petition the Webb Time Allocation Committee. I want to let them slew the telescope over and look at the other planet in the system. It's called SRAM. And when you look at that planet, James Webb Time Allocation Committee is going to charge her $1 billion. And she feels this great pressure because she really wants to get this right. What are the odds, given abundant, technological, sophisticated life on a very fecund planet called Hetarth, that there is life on the other planet in this binary system? Would you be surprised, shocked even, to not find life on the binary twin in the habitable zone of this hypothetical system?
It's overwhelmingly likely that if we find life that sophisticated on another planet, it's no longer going to be biological, because, we're looking at that life at some presumably random time in the evolution of life over there. If someone looks at Earth at some random time, they're not going to see us, right? We spent billions of years with nothing going on here at all. And then we spent some time with there was some bacteria living in the oceans. And then only very recently, in the last couple of 100,000 years or so, did we, Homo sapiens, start getting our act together, figuring out very recently now technology and building mega cities and flying rockets and stuff like that. And given the pace of AI, it's quite likely that this situation is not going to last for very long. So if someone looks back in a million years at Earth, they'll either find it all dead because we messed up somehow, or we will develop extremely powerful AI and robotic technologies that have let us go far beyond this planet to our galaxy and beyond. And most of that life is not going to be made of biological cells, right? So I would be very surprised if we see meat bags on other planets. I think it's way more likely that we'll see technological life, which might still be conscious and very interesting, that is evolved or developed ultimately by organic life.
Well, the reason I ask is, I think you taught me about Bayes' theorem and your house back in Philadelphia when you were there 26 years ago, and we were first getting to know each other, and you were so gracious. But obviously SRAM is Mars spelled backwards, and Hitre is Earth spelled backwards. So I'm really asking
the penny drops.
Okay, so now you got it. So the question I'm asking you is, should the non-observation of life on Mars, as far as we know, count as evidence against this ubiquity and this life maximalist approach that many of your colleagues and my colleagues have?
No, if we don't manage to go extinct or have a major civilizational setback in the next 10 or 20 years, we'll be on Mars, of course. It's just a matter of time. Elon is hoping to get there a lot sooner.
Well, I guess the question I have is maybe more the primitive life, the single-celled bacteria, slime mold, or people at Harvard. No, I'm just kidding. I love people at Harvard, Max. But the point I'm getting at is this concept of panspermia, which sounds dirty, but it's not. So here's a moon rock, which I owe you. I'm going to give you one of these. But I have a Mars rock also. I keep it under vacuum, and I don't let my kids near it. But Mars and Earth have been exchanging material for literally 3 billion years, and there have been life on Earth for 3.9 billion years. And so the fact that we don't, at some level, I just wonder, can we not start to put limits on how easy it is? When we think about the Drake equation, or we think about any framework where life already exists, you don't have to create life from ab initio, protoplasm or from hydrogen and helium. All you have is to take the pre-existing life and sprinkle it on another planet via gravity and impacts trajectories. The fact that we don't see life, and not yet, but we've, it sort of seems to me that you should be able to set some likelihood on how hard it is for life to get started, not how easy it is. We always just assume it's easy. Once life gets started, it's going to go everywhere. But I'm not so optimistic. So I'm curious. Yeah, the really low-level life, not the Elon, and above life.
My guess is that the fraction of all the planets that develops life sophisticated enough to invent some kind of internet is ridiculously small. I suspect it's actually the probability is less than 1 in a billion or something like that. So there's actually, we should expect us to be the only ones in the part of space that we can see in our observable universe that even got that lucky. I can explain why I come to that conclusion later if you want. If that's true, right, that does not imply at all that we should be surprised that we exist here. Because if inflation happened and space is infinite, then life still originated on infinitely many planets, and we shouldn't be surprised that we find ourselves on one of the planets where there is life. Any more than you should feel surprised that you happen to live on Earth rather than Venus with its nice 500 Celsius, 900 Fahrenheit weather today. But then we would expect that there was only probably one origin of life in the part of space we can see. Maybe life came to Earth via panspermia. Maybe it started here and went somewhere else, whatever, but it's all just one source. And then that would mean that however much we look in our telescopes, we're never going to see any other life in our observable universe. That it's really up to us what's going to become of our universe. So it puts a lot of responsibility on our shoulders not to flame out by doing something reckless.
That astronomically small number, can you explain how you got to that?
Yeah.
I agree with you, by the way. I actually think these maximalists like Adam Frank, who says, the probability would have to be below 1 in 10 to the 24th to, first of all, to see an alien civilization in the observable universe, in the history of the observable. Who cares, Max, right? I don't care unless they're 100 light years away, because I don't plan on really being around after 100 years rather.
You look healthy, though. You don't look a day older than during our last interview 4 years ago. So who knows?
Thank you. I'm sponsored by Rogaine and Minoxidil. So.
So there is this probability, let's call it P, that life smart enough to develop the internet appears on some random planet, okay? So that number P bakes in all the different things that could be difficult, like you have to get something simple going in the first place, you have to get maybe some cells or something, maybe it's multicellular life, and yada, yada, yada. You have to also get really, really smart, not be like the dinosaurs who spent over 100 million years without inventing the internet. All that gets lumped into that probability P. What is P? Well, we have no idea at first. So what we always do in science, if we have no idea, is we take a so-called uniform logarithmic prior, which is just geek speak for saying it could be 10 to the minus 5, 10 to the minus 10, 10 to the minus 15, 10 to the minus 20, 10 to the minus anything is roughly equally likely. And then we start using Bayes' theorem that you mentioned. We go in with this uniform distribution for what's in the exponent of that tiny number. And we say, well, if it were, less than 10 to the minus 16 meters, say, right, then we would have seen it already trivially. It's like closer than the nearest other star, basically. If it's more than 10 to the 26, it's already outside of our observable universe. So we would never see it. So there's actually a relatively small number of orders of magnitude where it would have to be for us to not have seen it already or been visited by it, and for it to not be relevant at all. And if you do the math just a little bit more quantitative than I said, you get significantly less than a 1 in 2 chance that there is anything at all within our observable universe. So again, what I take from this is, number one, we should feel like stewards of our observable universe, just to be on the safe side and take really good care of it so we don't mess up this great opportunity, because, as we'll talk about more later, even though so far life hasn't gotten very far, we're just on this planet here, we haven't even made it to Mars, right? We know enough physics now, and we know enough about AI that we know that it's totally feasible for us to spread life, not only throughout our solar system and our galaxy, but also to other galaxies and far, far beyond. So we might have a future billions of years from now when much of our amazing universe is really woken up and come alive with this incredible consciousness, having all these amazing experiences out there. Enormous upside. So let's be good parents, grandparents to that, and make sure we don't just instead flame out. The second thing to take away from it is you don't have to have too many nightmares that ET is going to come and kill you tomorrow, because if it were actually the case that there were a trillion other civilizations out there, and some of them pretty close, then most likely some of them will be so much more powerful than us in terms of their tech as we are compared to ants or cockroaches. And given that we're not always so nice to cockroaches, that's not a good situation to be in if we are, as humans, the cockroaches, that we're doing all our poetry and building beautiful cities and writing and trying to develop wisdom, and then some other civilization comes and just we need your atoms, move over. I actually prefer that we're the captains of our own ship here and have more agency over our own destiny.
Yeah, and certainly, although I agree with you about stewardship, but I want to remind you the year that we met, 1996, 1997, there was a discovery of a meteorite in Antarctica, where I've been twice. And this meteorite was taken all the way to the White House, where President Clinton said, "This rock speaks to us across the generations." And if the results are held to be true. Now, 99% of the people, except my audience, which is the most brilliant in the known multiverse, 99% of most people never knew that actual result was retracted. In other words, they've been living with this misapprehension for 28 years or what have you, that actually life was discovered and it was microbial, it came from Mars, and in fact, that's not true. And yet we don't treat each other any better. We haven't looked to be better stewards. Arguably, we're worse. We treat the planet worse. We treat the galaxy worse. I mean, Elon, for everything that he's doing, I talked to him briefly on the podcast via Twitter 6 months ago. And I asked him about, the impact of Starlink on astronomy. And he's like, "Oh, we paint them black." And I said, "Well, that's great, but it doesn't help us microwave astronomers. They're still above 300 Kelvin, and they're still spraying, in Q-band, as you know and love from your work with QMAP many, many years ago." But the point, Max, is that we don't treat each other better. And nothing arguably has gotten worse. So are you optimistic about the discovery of life, should it happen in our lifetimes, our children's lifetimes, that it would actually make that difference to make us better stewards of our cosmos?
I'm a bit cynical on this one. Yeah, I think discovering extraterrestrial life would probably not make us any nicer. I'm, however, fundamentally optimistic about human nature in the sense that I think it's totally oversimplified to say, oh, there are good people and evil people, and it's like a fairy tale and Little Red Riding Hood. And what I think is really going on instead is that you can take most people, and put them in a society in a context where the incentive structure brings out the worst in them, or where it brings out the best in them. So what I really hope we can do is create a society which is such that it really does bring out the best in all of us, and then we will actually be much nicer to each other. We have the potential to all really be nice to each other if we create a society that brings out our best sides. And that's one of the things I'm so passionately fighting for in my activism work. Besides, it's totally separate from this nerdy science research. We have a lot of history with this, you know. Even long before we were doing official nerdy science, Darwinian evolution invented some mechanisms to bring out the best in us. We have instincts like compassion. If someone walks down the street and or walks down a path in the jungle and there's a little baby there, they're probably going to stop and help it, right? We have love, we feel inhibitions to being unnecessarily violent. Even people in a bar fight are mostly not going to actually kill each other, even if they do some dumb stuff to each other. And then as society progressed a little bit further, we also invented gossip, which was a very powerful set of incentives to bring out the best in us, because people who mooched or lied or cheated got socially punished. They stopped getting invited to parties and people didn't help them as much. And as society got still bigger and we had to deal a lot with strangers, we invented a legal system, again, to give us incentives to, you know, bring out the best in us. And I think we've totally not maxed out on this. It's clearly possible to create even better incentive structures, not just for humans, but also for corporations and public figures and so on, public officials, politicians, to bring out the best in everybody so that we can actually flourish together. By the way, Brian, just coming back to aliens, can I say one more thing about aliens? So I've been quite fascinated by the recent surge in UFO discussions and evidence in recent years, or the more politically correct UAP acronym that the US military now likes to use. At face value, of course, one could take that as more evidence that there is extraterrestrial life, but I read a fascinating article a while back which made a completely different conclusion from this, which I just want to throw out there if you haven't come across it, which is that, so he was arguing that a very likely explanation for this is that actually our military and the Russian military and maybe other militaries as well are quite deliberately building surveillance craft, flying spy vehicles, etc., to look like UFOs. And that would make a lot of sense, because then when people on the other side see them, they get mocked and ridiculed and not taken seriously. There is arguably quite a statistical overrepresentation also of these UAP sightings near military bases and military exercises, etc. And if you look carefully at a lot of the sightings, even though you see these crafts that look really weird and UFO-like, in many cases they don't actually have flight characteristics that violate any known laws of physics. Sometimes they don't actually go that crazy fast, for example, or accelerate crazy fast, and are quite consistent with things you could build. If you put the brightest minds of the most powerful nations' armed forces into building cool spy craft, right, and just trying to make them look like UFOs, they could do a pretty good job.
That's a very interesting hypothesis, and it's of course completely, you know, forbidden for our government to say experiment on our own soldiers, right? No, of course not. They do it all the time. My brother-in-law is a former, you know, Navy SEAL type commando. He's been waterboarded multiple times by the U.S. government and as part of his training.
Really?
Oh yeah. I mean, not to the level of, you know, death, but I mean that might be. That's only what he told me, Max. I mean, in other words, he does a tremendous amount of stuff that he probably can't tell me about. He operates in Area 51, you know, quite frequently. And we know for a fact that the government does all sorts of, you know, they're called psyops, and we even do it against our enemies. We certainly have to test it and train it. And a lot of these sightings I've had on, you know, many of the major eyewitnesses, like pilots, you know, and so forth, that claim to witness it, and people that are in the media nowadays about this phenomenon. And so, yeah, it's a very interesting thing. I think a lot of it can be explained culturally, but I always make the point, maybe you'll agree with me, that no one would be more excited than someone like you or me to get access to the physics of the 29th century or what have you, and just short circuit and leapfrog into that domain of just imagine what we'd know. Assuming, they don't choose to have us for dinner.
Brian, though, on a positive note, you might just get access to the physics of the 29th century, within the next decade anyway, even if we don't get it from aliens, right? Because if we build artificial general intelligence and superintelligence and survive it, then it completely collapses this timeline, right? So many things that we thought were going to take another 900 years or 9,000 years to figure out, because that's how long it would take a human civilization to do it, maybe can be figured out in 9 months or 9 weeks.
Yeah.
By AI.
Max, thank you so much for this fascinating conversation on cosmology. Now I ask the listeners to please join us for part 2. But to get part 2, you're going to need to subscribe to my mailing list at briankeating.com/list. So head over there. You'll get a link to enjoy the second part. Thank you, Max.
It's been a great pleasure, Brian.